Sampling distributions of sample means. As an introduction, in modules 7 and 8, we used sampling distributions of sample proportions to estimate or test a claim about a population proportion. In this module, we will focus on sample means from random samples. In the first part of this lesson, we will recall what we know about sampling distributions of sample proportions. We will use these ideas to learn about sampling distributions of sample means. Try these. Election data proportions. The dot plot below shows the results from an election in an imaginary city. A computer simulation formed 200 samples of size 50. A sample proportion was calculated for each sample. The sample proportion represents the proportion of voters in the sample who voted for candidate A. The collection of sample proportions in the dot plot is a distribution of sample proportions. So here we see a dot plot. It says measures from sample size n equal 50. On the horizontal axis, you can see the numbers go from 0.3 on the left all the way to 1.0 on the right, and all of the dots that we have are somewhere between those. Question 1. What does a dot represent in this distribution? We can actually find the answer to this in the paragraph right above the dot plot. A sample proportion was calculated for each sample. The sample proportion represents the proportion of voters in the sample who voted for candidate A. That's what one dot represents. The proportion of a single sample of 50 that voted for candidate A. Moving on to number 2, use the dot plot to pick a single number estimate for the population proportion of voters in the city who support candidate A. Explain why you chose this estimate. Just thinking of what we've seen about representative values, it might make sense if we just choose a number that seems to be in the center of this distribution. If we try to cut these dots in half, it seems like maybe 0.6 would be a good representative. So 0.6, and explain why we chose this. It's a measure of center. The simulation was conducted 2 more times, but using different sample sizes. In each simulation, 200 samples were collected. One simulation used samples of size 25, the other simulation used samples of size 100. Histograms of these values are shown below. On the left, it says measures from sample size X, and we can see the histogram there. We've got bars that go down as low as about 0.35 and then up to about 0.8, say 75. And then on the right, measures of sample size Y. Here the bars go as low as about 0.475 and up to about 0.75. It also looks like the bars for the first graph on the left are a little wider than the bars on the graph on the right. Question 3 asks, which histogram do you believe represents samples of size 25? Which histogram represents samples of size 100? Explain why you think one histogram has a sample of size 25 and the other has a sample size of 100. From what we've seen over the last 2 modules, when we have a larger sample size, we have less variability and the distribution narrows. So because of that, the graph that is on the right, that would be the one with sample size 100, because the distribution is a lot narrower, not as widely distributed as the one on the left. And as an explanation, with larger sample size, we get a narrower distribution. All right, moving on. Now we look at election data, means. Imagine that we want to examine the amount of time it takes someone to vote. We call this voting time, and it is the number of minutes between the time when a person arrives at the voting station and the time when the person's vote is cast. In fact, we would like to know the mean voting time, that is the average amount of time it takes a person to vote. To explore how we could find the mean voting time, we have created a simulation. 200 random samples were simulated. Each sample contained 50 people with various voting times. The mean voting time was calculated for each sample. The voting time is given in minutes. The sample means are plotted below. Just for some details as a language tip off to the right, in the U.S., many people vote at voting stations in schools or other public locations. A voting station can be a booth or simply a table where a person reviews the candidates and chooses one. A vote is cast when the person turns in his or her vote. So this dot plot, again, if we look at just some of the details, dot plot of voting time sample means, n equals 50, so each sample has 50 people. And then we have time in minutes as our horizontal axis, as far down as 16 minutes on the left and up to about 20 minutes on the right. Question number 4 asks, what does a dot represent in the dot plot? So this is similar to what we saw in an earlier question. If we look above, each sample contained 50 people, and the mean voting time was calculated. Those sample means are plotted below. So each dot just represents the mean voting time for one sample of 50 people. Question 5, review the dot plot. Write down a single number that is your estimate of the mean amount of time it takes an individual to vote. Explain why you chose this number. Again, if we think of what we saw in an earlier question, it would make sense if we use a measure of center. So maybe if some way of splitting this data down the middle, maybe something like 18 minutes could be a good estimate. Number 6. The distribution above represents many samples of size 50. Suppose you were to run the simulation again using a sample size of 100. How would the distribution of sample means from samples of size 100 be different from the distribution above? Again, just like we saw in earlier pictures, the distribution would be narrower, and it would have less variability. Number 7. We have been plotting the mean voting times from all the samples. Suppose that you created a dot plot with the individual voting times of all 50 people in one of your samples, not the mean voting times. In this case, each dot would represent a single person and how much time it took them to vote. How would this dot plot differ from that of the distribution of sample means dot plot? Hint, think about the center of the distribution and variability. What we might want to think of first is the variability. If we're just thinking of all of the people and their individual voting times, we could have voting times that are very different from each other. So we might suspect that there would be more variability. And also as a center, remember that each of the dots that we had in the above dot plot, these are all sample means. So each one of these represents a center of a sample. And if you look at the distribution of all of these, on the far left, we've got a dot right at 16 minutes, which means that's the center of a sample of 50 people. We also have a dot up above, right above 20. That's on the far right. That represents a center of another sample of size 50. But a lot of the data is still gathered around this estimate that we had in the middle of 18 minutes. So many of them would still have a center that is close to 18 minutes. So there's more variability, so possibly a wider distribution. And we could also say most centers would still be near 18 minutes. But of course, there would be a lot of variability in those centers as well. So now moving on, collect a sample. We will now continue our investigation of the sampling distribution of sample means. This time we will use data about acorns that were gathered in Austin, Texas. This data can be found at the end of this lesson in the Acorn Mass Supplement. If you actually flip a couple pages, right at the end of the lesson before the take it home, you'll see there are 2 pages. We're going to be referencing this in just a little bit. 2 pages of Acorn Mass organization here, and you can see it all goes up to 400. These are 400 different acorns and their weights or mass. So going back to where we left off, the students in Austin who collected this data were interested in acorns because acorns are the seeds of oak trees. In Texas, oak trees are important to the overall health of the ecosystem. Many birds and small mammals eat the acorns that come from oak trees. A decline in the growth of new oak trees could have a serious impact on local animal and plant life. Botanists, scientists who study plant life, are especially interested in knowing the weights of acorns in a region. Botanists use information about the weights of acorns to help them predict the future growth of oak trees. In this exercise, we will explore the data to estimate the mean weight of the acorns in this data set. Number 8, start by randomly selecting 9 acorns in the acorn mass table. Use a table of random digits or a random number generator to select the 9 acorns. So what I'm going to use is a website called random.org. And I'm going to generate 9 random integers. And I want those to be between 1 and 400. So I've already done that, and I'm just going to write them in order. 55, 142, 155, 187, 194, 228, 283, 288, and 309. So these are my 9 random integers. And what I'm going to do next is match these up with an acorn weight on that supplement. So for example, acorn number 55 would be the first one that I would want to look at. So going to my table, I would find acorn number 55, and that's right here. And it has a mass of 4.6 grams. So back in the table that I've started, I'm going to write down 4.6. So I'm going to keep doing that for the rest of them, and I don't want to scroll up and down over and over, so I'm just getting a table from somewhere else. Here's the rest of those acorn masses. So for acorn number 142, 4.4 grams. For acorn number 155, 4.1 grams. For acorn 187, 2.5 grams. For acorn 194, 2.8 grams. For acorn 228, 3.8 grams. For acorn 283, 3.6 grams. Number 288, 2.3 grams. And 309, that is 4.1 grams. All right, part B. Calculate the mean weight for your sample of 9 acorns. This mean weight will be X bar. That's the symbol that we had for Math 21A. This is the sum of all X values, in that case, all of our weights, divided by how many there were in this sample. So I'm just going to add up all of those weights, and then we're going to divide by 9. So the sum of all of those weights is 32.2, divide by 9, and we get approximately 3.578 grams. Number 9, 10 random samples of 9 acorns were collected. The mean weight of each sample was calculated. These 10 means are plotted below. Each dot represents a sample mean. Add your sample mean to the dot plot. So ours is 3.578, which is a little bit between 3.5 and 4.0. And in fact, it's a little close to 3.6, which would be a dot like that. So on the horizontal axis, you have numbers from 2.0 on the left, 5.0 on the right. 3.5 is in the center, so the dot that I just plotted is a little bit to the right of that. If you have time, repeat the process of randomly selecting 9 acorns several times. Calculate the mean weight for the sample. Plot the sample mean on the distribution above, and then write the value of each new sample mean below. So if you'd like to do this again, here's another 9 random numbers. 59, 99, 159, 239, 265, 278, 358, 364, and 391. So you can match that up with the table of acorn weights, find the mean weight X bar by adding up all of those X values, and then dividing by 9. And when you finish that, you can plot the dot up in that dot plot above. But we're going to move on. A dot plot and histogram of the mean weights from 500 simulated random samples are shown below. Each sample contains 9 acorns. The values are shown in grams. So again, we have 500 dots here. Each dot represents a sample mean where the sample size was n equal 9. You can see that we have numbers on the left around 3.00 and then all the way to the right near 4.75. Right below the dot plot is a histogram, just organizing that same information in a different way. Number 11 says, in the dot plot of the distribution of sample means, what does a dot represent? This is the same sort of answer we've seen before. That is a single sample mean weight for 9 acorns. So we could say a sample mean weight for 9 acorns. And here is your code word for this lesson. Acorn. Number 12. Imagine we want to estimate the mean weight of individual acorns collected by the students. Part A. How could we use the distribution of sample means to make this estimate? Hint, think about what you can see in the distribution that might help you make a good estimate. So again, just like we've seen before, how about we use the center of the distribution? This would be the mean of the sample means. So looking at our dot plot above, if we choose something that looks to be in the center, maybe something like 3.75 grams. Number 13. Sample means are estimates of population means. So, a distribution of sample means is a distribution of estimates. Any deviation that exists between a sample mean and the population mean is an error. This is why we call the standard deviation of all sample means the standard error. Part A, estimate the standard error of the distribution of sample means from the previous problem. This is a little bit of a tricky thing to do. We had some trouble with this, maybe you might remember in Math 21A. But if we think about some things with the normal distribution, that might help us. We learned in Module 6 that where we had an inflection point, where the curve went from concave down to concave up, that would be one standard deviation away from the mean. And it looks like for our graph, that happens at 4.00 on the right, if we're using that as a guide. That's 0.25 away from the center, so that could be a good estimate for the standard error. Part B, compare the standard error to the standard deviation of the 400 individual acorn weights. Do you think the standard deviation is larger, smaller, or about the same as the standard error? Explain your answer. So when we think about this, again, let's think of up in this dot plot, we're looking at 500 samples of 9 acorns each. Whereas what they're asking about is the standard deviation of just 400 individual acorn weights. As we've seen before, we might suspect there'd be more variability in these 400 individual acorn weights. So we would think that maybe the standard deviation would be larger. More variability in individual weights. Number 14. The simulation was conducted 2 more times using different sample sizes. Each time 500 samples were collected. One simulation used samples of size 25 and the other used samples of size 100. The results are below. So again, we're looking at some histograms here. On the left, we see wider bars in a wider distribution, and on the right, we see skinnier bars in a skinnier distribution. Question A, which of the above graphs do you believe represents samples of size 25? Which graph represents samples of size 100? Explain your answer. Just like we saw before, size 100 would go with the narrower distribution. And as an explanation, with larger sample size, we get a narrower distribution. Part B. Estimate the standard error of the 2 histograms above. Just like we saw a little bit ago, it might make sense if we think of a normal distribution with these, as these look approximately bell-shaped. And maybe we could just estimate where the inflection point, where the graphs are changing from concave down to concave up. But what we should at least expect is there would be a smaller standard error for the size 100 graph. So you can use ideas of center and trying to estimate how far to that inflection point. With what we see on the size 100 graph, maybe that could be something like 0.15 maybe. And then for the size 25 graph, that would be a little bit more, and maybe that might be 0.25. And finally, part C. What relationship do you observe between sample size and the value of the standard error? Like we've seen before, as sample size increases, standard error decreases.